Hello everyone. So we are in our 8th tutorial class. In this we will be discussing the RF and cold plasma devices, their principles, designs and discharge characteristics. So the topics covered: RF plasma devices, cold plasma devices, kilohertz, megahertz and RF region. Of course megahertz is RF only. Now DVD and CCP systems, discharge characteristics and comparative features. So principles of RF plasma generation is summarized over here. You know, there is RF plasma in 13.56 megahertz, that is a industry standard. So this type of sources are available in market. You can generate other than this 13.56 megahertz. There this RF plasma, thermal plasma devices are usually operating at around 3 megahertz. So this device, what you are seeing on the right side, this is basically an RF plasma torch operating in our lab at 3 megahertz. So how it operates? I just summarize here. So you apply an RF current, radio frequency current through this coil, and you should have an idea that how many turns. It is not like solenoid coil is where you have thousands of turns. It is not like that. It is having only 1, 2, 3, 4, 4 turns. That's it, and that is sufficient to do the job. So you must remember that the kind of configuration it is having. So this is a tutorial, so you should have the practical experience. Now the RF current, that when it just goes through, it will produce a magnetic field. And where it will be? It will be along the axial direction. Now the current is switching once clockwise, then anti-clockwise. So magnetic field is also switching, and in which direction? It is in the axial direction. Now when there is a del B del D component and B is switching in the Z direction, there is something Maxwell's equation which says that curl E will be equal to del B del T. Curl E is equal to minus del B del T. So so that electric field generated due to this changing magnetic field will be in the azimuthal direction, curl of E. And that this changing electric field, curl of E, because B is switching, the electric field also will be switching. One will be in clockwise direction, another time it will be anti-clockwise direction, and when it is switching like that, it will induce the electrons to get accelerated accordingly, and they will collide with the surrounding gas atoms, they will ionize them, and electrons will come out, and your plasma will be formed. So this way your RF plasma is generated. Now I come to the other RF plasma devices. So the inductively coupled plasma, ICP. A coil is wrapped around a quartz tube and RF generator and matching network. This may be at lower pressure, and you will get a much kind of non-equilibrium plasma if you are doing that in at low pressure regime. But in high pressure regime, what you have just seen in our previous slide, the this kind of RF plasma will be generated. This is at atmospheric pressure, and the temperature here, it may be around 10,000 degree Kelvin or so inside, and it is hold inside a quartz tube, double walled quartz tube, that chilling water is passing through in between region. Now advantage of this ICP device is that they can provide you high energy density, it can be stable, controllable discharge. Discharge is quite controllable, and effective for nanosynthesis and coating. Because of the high temperature, you can go through this top down approach and then bottom up approach to you can utilize both, because The top-down approach is when it is entering into the plasma and getting disintegrated into atoms and ions, and then when they go the downstream, they collide with each other, and from the top, bottom-up approach, they starts forming, starts nucleation, and finally reach a size which is usually in the nano range, and that size distribution you can control by controlling the gradient in temperature, and of course the input power and all this thing will decide the ultimate process scenario. Then coming the capacitively coupled discharge over here. So the thing is that you are using parallel plate electrodes, and RF power is applied between these two plates. So they are usually used in processing industry. I will be coming to that. I have one slide on the applications. So the disadvantage of this RF kind of devices that they require, the CCP devices, they require vacuum, and RF, when you are using RF, requires shielding, because this RF can propagate. For example, if you are operating an RF device in this room, some 2-3 rooms away also the effect can be seen. And usually the RF systems are not as simple as the arc systems, they are a bit complex. Now when you are going for these cold plasma devices, they operate nearly room temperature 300 to 500 degree Kelvin, and they have higher electron energy and low gas temperature. So that is a specific area where you really require that. You need to touch that by hand, like biomedical application, but you require a very high electron energy so that you can generate the radicals at certain concentration which is sufficient to impart the effect that you want to see on the organisms. Now here I have the frequency range of this cold plasma. They can operate in kilohertz range, megahertz range, and standard RF frequency like 13.56 megahertz. So when it is operating in the kilohertz range, usually they are going for this DVD and corona discharges. When it is a megahertz, you have customized it between 1 to say 100 megahertz. You can develop the CCP device and low pressure cold plasma devices. I have written the red in red, the RF thermal plasma devices. They operate in say 2, 3, 4, 5 kilohertz, around that. And there you are generating really a very high temperature plasma. It is not a cold plasma, it is a thermal plasma. Using low pressure regime, you can generate the cold plasma as well using the same technique. Now 13.56 megahertz cold plasma devices are being used for quite some time for surface treatment and etching purposes. Now DVD and CCP I have compared here in these two columns, that in the DVD one or both electrodes are covered with dielectric barrier discharge, that stands for DVD. So there is dielectric, either one or both the electrodes are covered, operates at atmospheric pressure, that is very important. DVD operates at atmospheric pressure and generates micro discharges, prevents arc formation. They are used in surface sterilization, ozone generation, plasma agriculture, like that. Whereas the CCP, the electrodes are connected to the power directly, and they discharge via capacitive electric field, and low pressure operation is a necessity in these devices. So they are used in your thin film deposition like PCVD and plasma etching. What you do actually, your reactive gas, which is responsible for the thin film deposition, you basically discharge that in the you release that in the discharge zone between the two plates, and that breaks the reactive gas, and allows the deposition to occur on the substrate you are interested in. So this thin film deposition is there, and then plasma etching, semiconductors, this can act as a very suitable device. Now as far as the discharge characteristics are concerned, I have summarized over here. ICP, the gas temperature is high, electron temperature is also high. They are mostly operating in your this thermal regime. This is the kind of scenario when you operate that in the thermal regime at atmospheric pressure say. Then pressure is variable, but if you go to lower lower pressure, you can generate ICP at much lower temperature, lower gas temperature. Electron temperature still may be quite high. The discharge mode is inductive, and if you are operating in at atmospheric pressure in the thermal regime, then of course the temperature is also high. Then CCP, the gas temperature is low or medium, and electron temperature is high anyway. Pressure is low. CCP devices are usually operated at much lower pressure, say 10 to the minus 2 to 10 torr, and the discharge mode is capacitive coupling, capacitive discharge. Now, dielectric barrier discharge, gas temperature is really low, you can touch it by hand. Electron temperature may be high. Electron temperature is may be high, means it can easily be 2 to 4 eV, like that. And then it can operate in atmospheric pressure. That is another advantage of DVD devices. They usually discharge goes through micro discharges. The plasma happens to micro discharges. And finally, the corona, the gas temperature is low, electron temperature is medium, it is not very high. It also can operate at atmospheric pressure, and the discharge mode is streamer or glow. So, this slide actually summarizes the type of discharge characteristics that is available in this ICP, CCP, DVD and corona devices. Now, the distinctive features I emphasize it once more in this. DVD, it is non-thermal, short-lived filaments, no electrode erosion. That is the usual feature of this. CCP, uniform plasma, low pressure, high frequency operation. Then ICP, this RF plasma you are using, then high density, thermal plasma, and they are usually used for synthesis and coating. Then corona, they are using usually sharp electrodes, the point discharges, and they are usually at a very low currents. So, these are some specific features of this DVD, CCP and ICP and corona discharges. So, these are very typical some features that you can keep in your mind, freeze in your mind, so that whenever you see such kind of devices, these are the typical features that you are going to have. Of course, there will be exceptions, and you can deviate from one design to another design in the same device sometimes, and you can get a feature which is different from usual features. So, they are actually the research areas where people are trying to explore. I am not going into all those details, but these are the typical features that you will find in the kind of devices that are discussed here. So, all the devices at a glance, I can say that pressure, DVD is atmospheric pressure, CCP at low pressure, and ICP low to atmospheric pressure. Then frequency, DVD is kilohertz to megahertz range, then CCP is 13.56 megahertz range, or you can use a variable frequency range. Then ICP 13.56 megahertz is there one, which is commercial standard, and you can make custom devices as well. Gas temperature in DVD it is low, CCP it is low to medium, and ICP it is high. Electron temperature in DVD it is low, in CCP it is high. Sorry, gas temperature in DVD it is low, in CCP it is low to medium, not high, and ICP it is high. And the electron temperature is high in all the cases, in DVD, CCP and ICP irrespective. Application wise, this DVD specifically find the application in biomedical areas, CCP in etching, and ICP in coating and synthesis. These application areas are basically marked by these devices. Whenever you go for the application in biomedical area, you usually go for these DVD devices, and when you are etching, you usually prefer the CCP devices, and when you want the coating or synthesis in very pure form, because these ICPs are electrodeless, so you don't have any contamination from the electrode, because electrode is outside the quartz tube and it is not coming never in contact with the the plasma that has been formed. So, you get a pure kind of plasma discharge. So, pure synthesis is possible there, and this biomedical application always require a low gas temperature, so that is why the DVD is used over there. And CCP, when you are going for etching, you are not really much bothered about very low temperature, little higher temperature also will work, and rather it will work better. So this CCP is good for etching. Okay. But electron temperature, because they are low mass, so I have told it so many times, so they are highly mobile and their temperature easily goes high. Now I come to the numerical, 21st numerical, this is one. So where we want to know the plasma frequency. It is really curious we feel curious to know what may be the frequency of the cold plasma devices, plasma frequency. When what we are going to apply for, say, biomedical applications kind of thing, what may be the plasma oscillation frequency. So suppose the density is 10 to the power 11 per centimeter cube. So usually they are presented in per meter cube nowadays. So you should multiply by 10 to the power 6. So it will be 10 to the power 17 per meter cube, the number density. And there what you see that the plasma oscillation frequency, this is the linear frequency, 1 by 2 pi root over n square by m epsilon 0. You put the values that has been given in the numerical. So this 10 to the power 11, so it is 10 to the power 17 per meter cube. Then E is the electronic charge, epsilon 0, 1 by 4 plus epsilon 0 is 10 to the 9 into 10 to the power 9. So accordingly you can use that, and then mass of electron in 9 into 10 to the power minus 31 kg. You put all those things and you see that the plasma oscillation frequency in case of cold plasma coming in the gigahertz range. So that is what we are interested in, to understand the plasma frequency in cold plasma. So when you are going to deal with the cold plasma devices, this is the kind of number density, and you should keep in mind, okay, the plasma oscillation frequency comes in the gigahertz range. So that's why I just introduced this numerical, so that you have some idea about the kind of this plasma oscillation frequency that is there in the cold plasma devices that will be handling. Now this is numerical 22. It is meant to understand the typical ion transit time in plasma. So ions moves, we all know that in the sheath region basically there is a there is a field which drags the ion, because the wall gets negatively charged, so it feels applies a bias, so it keeps the electrons away and tries to pull the ions towards that. And in a plasma device, suppose you have made a large plasma device, the major voltage drop occurs near the sheath region. So here one example where we are trying to 1 centimeter, so it is just 10 millimeter near the wall, and there one see that a voltage drop of 50 volt occurred across that actually. And then the question is, how long an argon ion will take to travel that distance? So we need to definitely find the velocity. How do we do? Because you are getting a drop of 50 volts, so the energy that it will gain when it passes through that drop, it will be Q into V, so Q into 50 volt. Now that will result in some velocity, half mv square. So if we assume that the ion is at negligible velocity before it enters that region, so we can assume that this is the velocity that is going to get after it covers that voltage drop. So half mv square is equated with qv, and there I am getting a velocity twice qv by m. So t time taken will be distance by this velocity what is found over here. So I just get v substituted over there, and we get the velocity as 4.9 into 10 to the power 3 meter per second. So the velocity that root qv by m, it is coming to be around 4.92 into 10 to the power 3 meter per second. So the time that will be required is just you divide this velocity, and 1 centimeter means 0.01 meter. So you just divide that by the velocity and you get 2.03 microsecond. So now you keep this in your mind that it is about a microsecond that an ion takes to just cause that region. So the phenomena are happening, this transit is happening in the scale of microsecond over there. So this all we are getting from very simple, this numerical exercises, we are getting some idea. It may be microsecond, and maybe order of magnitude vary here and there. So it is, the order is that it is microsecond. So that is what is important, and to keep that impression in your mind that when an argon ion, it is quite heavy mass, So compared to your electron or compared to a single proton, it is quite heavy, and this takes that much time, that is microsecond. Then this is our next tutorial where we want to find the gas temperature rise if 1 watt is absorbed by argon gas. So this is the kind of wattage absorbed when you are operating a cold plasma devices, and specific heat of argon is given as this 520 joule per kg Kelvin. This is required, because when you are going to apply the cold plasma devices, we are always bothered about it should not raise the gas temperature very high. And if it raises, how much it can raise? And what is the dissipation? Usually it is of the order of 1 watt kind of device when you are applying a cold plasma device for medical application. So there, this Q equal to mCp dt, that is you have read in your school days. So the temperature rise is Q by mCp. Cp is the specific heat, m is the mass. Now here what we have given that mass flow rate is 0.2 gram per second. So it is a flowing mass, 0.2 gram per second. So that is given over here, and then Q is mCp delta T. So it is coming to be around 1 joule. So then delta T, what is coming? Q by mCp. So this is Q 1 joule divided by this 0.002, this mass, and this is the specific heat, that is 520. So it was 1 watt means 1 joule per second, right? So that is what 1 joule Q, and the rise in temperature is coming from here is 9 Kelvin. So this is the delta T. So it is in degree centigrade also the same thing will be there. So when you are dumping 1 watt, you are raising the temperature by only 9 degree centigrade. Okay. So 10 degree centigrade kind of thing, the 9.6 is there. So it is not much. So if you are your gas input is at say 27 degree centigrade, the room temperature, then it will be maximum 37 degree centigrade if you are putting 1 watt of power in that. So that is within your bearable limit for limited time application. So with this I stop this tutorial, and we'll be going to our next tutorial in the next class. Thank you very much.